Hello guys, welcome back to Insa Electronics. So in today's episode, let's take a look at this 2000 watt hot air gun that is made by Eastman. Now this one is actually a dual stage temperature controlled hot air gun. It has two different modes for two different fan speed and two different hot temperature modes. You can see the switch has two different modes. The first mode will give you for 50 degrees of temperature with 300 liters per minute of airflow. The second mode will go up to 600 degrees of temperature with 500 liters of per minute of airflow, little bit more speed, little bit more temperature. And because the body is made with plastic, they decided to go with a standard 16 amp 2-pin plug, although they could have just used a standard 3-pin plug because the hot air portion is actually made with metal, and that is the part that hides the 230 volt right underneath that. When it is opened, you can see it's a pretty minimalistic construction. There is not a lot of things that is inside compared to the other hot air gun that I have, and I will be taking part in the next video, which is this one. It is a Power Trucks 2000 watt unit. It has a rotary knob for adjusting temperature, so it has to be something different, which we will see in the next video. This one has very minimalistic things going on inside. You can see the AC mains wire coming in, and one wire goes straight to the switch. The negative or the neutral, which is the white wire in this case, goes straight to the coil. I will explain everything in the schematic, so don't worry about that. The switch is actually a special thing. The live that is getting at the input, it's a common input and two different outputs based on which position the switch is actually in. So if the switch is in position number 1, which is for the low temperature mode, the mains is getting connected to the red colored wire, which is on the top position. Alright, so first mode, the mains get connected to the top one, which then goes to the first set of coil. And when it is in the switch number position 2, which goes to the bottom blue color wire, which then goes to the secondary set of coil, which is used for the higher temperature mode. Alright, so in total this has around 3 sets of coil, which again I will explain all those things when it comes to the schematic side of things. There is a 0.1 microfarad 275 volt plus X2 capacitor right there, which is not there for any kind of smoothing purpose or anything, and it really serves a purpose in the whole running of this thing. I shall explain all those things in the schematic. First of all, let's take a look at physical overview and how the hardware side is put together. Alright, so when we take apart the screw, we can see the metallic part and the motor side that was held together with its own screws, and the motor part was held onto the body with its own screws just to prevent it from moving around. The motor is a 24 volt DC motor with its own PCB for the rectifier and the smoothing capacitors. It has an impeller inside which sucks air through the ventilation on the bottom side, which I'll be showing you in a couple of seconds. Let's open it and I will give you a proper view of this impeller. You can see it right there. So it makes use of the centripetal force or centrifugal force, whichever way you want to call it. When it spins, it sucks air from this ventilation over here. It sucks in the air from that, and it pushes out through the front portion right there. So while taking a look at the PCB on the motor, we can see a couple of capacitors and 2 diodes on this side and 2 more diodes on the other side, which clearly makes a full bridge rectifier. Those capacitors are connected to the ground just to make sure that the switching noise, the brush noise, don't really get back to the AC main circuit. Although it's really small, but they're still trying to minimize the noise that is getting back to the AC side, which is really a good thing to do when it comes to the motor loads like this. While taking a look at the heater coil, you can see the metallic part will expose. If you take out the metallic part, it exposes a microfilm sheet, which is used as an electrical insulator but conducts heat, so it is there to prevent you getting a shock as a piece of rolled mica sheet. So underneath is what I said, like it has three sets of coil. You can see a smaller set of coil and a large roll of coil. Each has its own purpose, which we will discuss when it comes to the schematic side of thing. So yeah, that is that. You can see 4 wires coming onto the coil, out of which 1 is common and 2 will be going to the heater coils and 1 will go to the coil for the motor. Now don't worry about the connections this time, because I'll be explaining all of them in detail when it comes to the schematic side of things. So there is a thermal cutoff switch in between. You can see the small white block right there, that thing that is actually a bimetallic strip to prevent thermal cutoff. You can see it right there. So this is typical kind of arrangement that you see in an electric iron. When it gets too hot, it gets turned off. So that's the same thing. If something goes wrong, if the temperature goes beyond certain limit, the switch just opens and it restricts the amount of current that can flow through it. Essentially, it is a safety bypass switch. So speaking of which, the smaller set of coil, you can see over here there is a small set of coil which is the first pair, and that is actually the series dropper resistor for the motor. And this large pair of coil is actually not a single common pair, it is actually like a center tap configuration with a common in the middle and two different wires at the two different ends. Both of them will have a different power rating. Don't worry, that is what connects to the switch, and we will explain all those things when it comes to schematic side of things. So let me give you a running overview of this unit. So if I connect it and if I turn on the switch, you can see the coil gets red hot. Now the motor is spinning because this coil, you can see when I put it in the second mode, the coil gets even more brighter, the fan speed has almost suddenly increased, and that is because that glowing thing is not there for heating it up, but instead that is what it relies on for dropping the 230 volts down to the 24 volt that is required for the motor. Then again, the 24 volt AC is converted to DC using the built-in bridge rectifiers. I'll give you a side overview. You can see the thing is actually getting really hot, and the main coils are not getting hot because that is the problem with this unit. It's a dead unit. The coil is actually broken, so the main heater part will not run, and I will show you a demonstration of how the heater coil will look like if it was working. So I will do it with a different hot air gun, but right now let's move on to the schematic side of things. Alright, so now that you have seen how the hardware side of things are put together, let's move on to the schematic side of things. So first of all, let me tell you what are these things, and then I shall explain how it all works. And if you want to reverse engineer it, if you want to understand it by yourself, you can pause at this moment and you can figure out how it works by yourself. But allow me to explain. So these are the two wires that are coming from the AC main side, the white and the brown one. This is a switch that we have already discussed. It's a common point, and these are the 2 points. This is the first mode for the lower temperature. This is the second mode for the higher temperature. I hope everything is in focus. This is the 24 volt motor, and these are the 3 set of coils which I have mentioned in the previous section. The two set of coils for the primary heating, the third section for the auxiliary heating, as well as for the DC series dropping for the 24 volt motor. This right here is the capacitor which you have seen, and inside the coil for the motor is the thermal cutoff switch. So now that is the physical overview of the schematic, let me explain how it all works. So let's assume that the AC mains is present, and you can see the neutral is going straight to the AC cutoff switch or the thermal cutoff switch, whatever way you want to call it. It is basically a normally closed type of switch. This is what typically found inside the electric iron. So if the temperature is increased beyond a certain point, it gets opened up, thus releasing the circuit, and the power gets disconnected. So it's interesting that they have actually placed the thermal cutoff switch right inside the coil for the DC motor. See that the motor is actually the essential thing in here, because without the motor, if the motor is not spinning up, then eventually within a few seconds itself the entire set of coils will run out. They will get burned out because there is nothing to cool it down. The heater is actually being cooled down every single time by this motor, and that is why the air is getting hot. As soon as it passes through the coil, which is red hot, it takes away the heat from it, and the motor is an essential part to keep the coils down to the lower temperatures. So if the motor for any reason stops spinning, the temperature gets really hot. Either this will get much hotter or these two will get hotter, depending on what kind of fault situation it is, which is enough to trigger the bimetallic strip in this thermostat to the off position, which will disconnect the whole thing from the neutral side. So the entire neutral will get opened. So the AC mains goes straight to here, and assume the switch position is in the lowest mode. Just forget this connection. Assume that the connection goes from here to the pin number 1 of the switch. That means it is in the 450 mode, 450 degree temperature mode. So what happens is that the neutral goes straight to the coil. and because this is in normally closed condition, all the coil will get the neutral. All right, so the neutral goes through here, through this coil, bypasses this one, goes straight to the AC main side. So the AC mains will come through here, the phase will go straight through the set of these two coils which will be in series and goes back straight to the neutral. So basically just two pair of coil connected in series and connected across AC mains. That is what the low temperature mode really is, because you are putting two resistors in series, the current flow through them reduces, and because the current flow has been reduced, the I square RT will actually reduce. That means the temperature will be lower. That's why the system will go down to 450 degrees Celsius when it is in the first mode, because both of them are in series. But at the same time, you'll be wondering how the motor gets the power, because the switch is now in this position. The motor does not have any power to ground. You're wrong, because when the switch is in this position, and these two pair of coils will form a voltage divider network. You can imagine it as a set of resistor here and as another set of resistor here connected across AC mains. There will be a specific voltage drop available at this point right there. So let's assume this is 120 volt, this is 120 volt across each of them. So when you measure this point with respect to ground, it will be 120 volts. This is just an ideal case, I'm saying, just for an example, not in the real life. So that 120 volts will go through this blue wire, and because this path is open, it cannot flow back to here. So it has to go through the motor, which gets rectified by the full bridge rectifiers. It goes out through here, and again the voltage will get reduced further through the secondary pair of coils, or let's say the third set of coils, and goes to the other side of the thermostat. So if the temperature is within limit, it allows it to pass through, so the motor will be getting the neutral as well. So the motor will start spinning. Because now it has to flow through two different sets of coil, the voltage reaching at the motor will not be 24 volt, it will be much lower than that. And that is the reason why the speed of the motor gets reduced, because now it has to go through this particular set of resistor, then it has to go through this particular set of resistor. So essentially, the higher the resistance, the lower the current flow, the lower the speed of motor, the lower the airflow. So that is that particular mode. Alright, so I hope that you have understood the first mode. And now let's talk about the interesting part of this thing, the second mode, which is the higher temperature mode. So when you connect it to the second mode for the higher temperature, the 600 degrees at 500 liters of airspeed, both the temperature increases and the fan speed also increases. That is because now you can see the neutral is again common for both the coils, and this is what I said as the center tap configuration, because you can see the common wheel is in the middle and two set of wires on the other sides. So it's like a center tap configuration on this side. So when the switch is in the position number 2, the AC mains goes straight to the motor, because it does not have to go through here. This is an easier path. So the direct 230 volt will be available across the motor. It gets rectified to DC, and it goes to here, and it has to go through only one set of resistor coil to the neutral. So this is the reason why when the motor is on, you as you have already seen in the previous clip, when it is in the switch position 1, this part is getting hot. You have already seen that. And when it is in switch position 2, it gets even more hotter, like from red hot to orange hot, because now previously it has more resistance in it, so it has reached only red hot. Now the AC mains is going straight to here, which means more energy is available, less resistance, more current. This thing will get even more hotter, because now it has to drop even more voltage across it to make it down to 24 volt. So it gets from red hot to orange hot. That means the voltage across this is higher, so the fan speed will increase. So that is the fan side powered. Obviously the airflow will increase from 300 liters to 500 liters per minute. Then comes the interesting part. Now this blue wire will receive the AC mains from here, and it goes to here, which is the first set of coil. So it's easier path, like go through here, goes to the neutral. So this will get really hot. Then at the same time, you can see this section over here. The AC mains is available at this point, so it has to go through here and through this capacitor to neutral. So essentially, when it is in the higher temperature board, all of the heater coils are getting activated, and just because this particular coil has to go through the capacitor, the temperature will be slightly reduced, because this is now acting as a resistor. In an AC circuit, the capacitor will be acting as a resistor. So let's say this is a typical capacity dropper power supply. Let's take an example for the capacity dropper power supply. This is what they are using at the input side. So the same application happening in this side, just to reduce the current down to a better safer limit, just to get the 500-degree mark. They have specified this particular value capacitor, although the voltage rating is much lower. It's just 275 volts, which is I don't recommend, or you always better use a 400 volt capacitor over here, but that's what they did, so I cannot do anything about that. So when it is a high temperature mode, this gets direct AC and this has to go through this capacitor, so both will get hot, although this will be less hot compared to this one because of the extra capacitance which is acting as a resistance. And at the same time, this coil is also hot because now there is no extra resistance to bring down the voltage across this one. So in the high temperature mode, everything is getting hot. So that is the higher temperature mode. And let me explain that this resistor here is actually used as a series dropper. They can actually use a smaller transformer to reduce the input voltage down to 24 volt, but that is not necessary. They can actually use a capacity dropper to bring the voltage down to 24 volt. That is not necessary, because this is not designed for any kind of efficiency. This is designed to dump the energy in the form of heat. So they don't have to care about producing heat or losing energy or wasting energy, because while being in operation, it is supposed to get hot anyway. So why don't just provide it with an extra boost of auxiliary heating with a pair of coils that can also act like a series dropper resistor. So that's the way that they found to get it done. So that is the whole circuit arrangement for this. It's really basic. Anybody can make one of these. If you want to make one of these, you can follow this thing. That's that on the schematic side of things. Now let me move back to the previous clip, and I'm going to show you now a working unit which is made by a company, Black Plus Decker, not the Black and Decker. It's a reputed brand. This is a Chinese brand. So in that one, you will see the coils getting hot in real-time action. So moving on to that clip right now. So this right here is the Black Plus Decker 2000 watt hot air gun with a different switch configuration. The bottom one is for the lowest temperature. You can see, since both the coils are in series, the temperature is lower, which is visible from the coil color as well. And when the switch is in the top position, which is for the higher temperature mode, both the coils will come in parallel configuration and much higher current is going to flow, and visibly the coil is getting much brighter. That means the temperature is also much higher. That is one reason why I don't want to point my camera straight in face of the hot air gun, because almost certainly it's going to ruin the camera, because at least nearly a feet away from this hot air gun, it is unbearably hot. So I don't want to keep it too close to the camera. So this is a side view of the same thing, just waving it past the camera just to give you a much better view. So yeah, that is the much better view. That is the higher temperature mode right there, guys. So guys, that's it for the working of a hot air gun. We have been through the hardware side, we have been through the schematic side, and yeah, that's it for today's video. If you have any doubts regarding this thing, just hit me up in the comments below, or you can mail me to my mailbox as well, and the email is in the description right below. So yeah, thanks for watching, guys.